Well, good afternoon, everybody. Hopefully, you all had a restful and warm weekend. Stayed inside. um, I don't really have any updates per se for class today. I did put a study guide in the exam folder. Okay, so if you're interested in that, um, that might help you kind of, so that you get a idea of what kinds of questions or what topics are going to be on the midterm. Okay. Just remember, don't fret too much about that because the midterm is open book, open notes. Okay. So you'll have the ability to double check anything that you're not sure about. Okay. So anyway, any questions before we get started? Okay. So recapping from last week, so we looked at rocks and minerals last week, okay? And this week we're going to transition to more of a practical application-based topic. Well, actually, it's pretty much what will be what we're going to cover from here on out. Okay, quick question. Okay, yeah, go ahead.
I heard something about there was like an earthquake in the ocean, but I don't know where it was located. If it was like by Australia or something. So I was wondering if they said they were on an alert about tsunamis. So I was wondering if there would be, like, is there a good chance there would be?
Yeah, most likely. Um, Depending on the size of the earthquake, if it's a bigger earthquake, then yes, definitely a tsunami, definitely a big one. But the smaller the earthquake is, it's still probably going to create a little bit of a tsunami, but it could kind of emanate as maybe like what you would get at the highest high tide of the month, spring tide. So yeah, I haven't heard of that. But I can talk about tsunamis as they apply to earthquakes. That would, if everybody wants that, because they are real interesting phenomena. All right.
All right, thank you. I was just wondering because we read about it in our book, so I was just wondering, that's all.
Yeah, yeah, and pretty much, all the major tsunamis that have happened in the past have been associated with pretty large subsurface or sub-ocean tsunamis. Okay, because they basically the energy waves they radiate out. But here's here's kind of the basic behind a tsunami. When you have a fault, and we're going to talk about faults today. When one moves in relation to another, what's happening is some form of displacement. And so usually what's going to end up happening is there's going to be one chunk of a rock shoved up or down, and that essentially creates a wave energy, okay? And that wave energy just keeps emanating out away from the earthquake itself until it reaches shoreline areas. Okay, so having said that, a tsunami is just basically energy waves. Okay, so let's go ahead and okay, here we go. Okay, cool. All right, so today we're going to talk about plate tectonics, and then earthquakes and Earth's interior. Okay, so chapters 4 and 5. So what I just talked about with tsunamis, we'll look at it today. So first, let's talk about plate tectonics, because really this is the process that drives a lot of the geological processes that we see in everyday life. Okay, but before we get to talk about the plate tectonic theory, we need to understand what happened before then, because this wasn't something that just came from thin air. Okay, so it had always been known, even in ancient times, that well, maybe not ancient times, at least up until the times where there were maps, that South America and Africa seem to have shapes in which fit together very nicely. Okay, and it wasn't, that concept was not understood, or at least it wasn't really explained well, or at least minimally, until 1915. But even then, it wasn't really explained well. Okay, so early 1900s was the hypothesis of continental drift. Okay, this was basically a guy that came along and he said, here's my thoughts on, what has happened in the past with movement of continental plates around, around Earth within the ocean basins. So he basically hypothesized that, and this is Alfred Wegener, he hypothesized that there's a big giant landmass called a supercontinent about 200 million years ago. He named it Pangaea, which it is still named today. And it is known now that, yes, Pangaea was actually a supercontinent, and there was one quite a bit older than it called Rodinia that we'll look at in a later chapter. But here, in this bottom picture is Wegener's version of Pangaea, and then up here is a modern schematic of what Pangaea looked like. So you can see it's actually not bad. He did pretty good in that respect for having very little information. But so he had the basic concept correct, that these plates move around and then they had come together at one time. But what he lacked was a viable explanation of why it happened. So he argued that these continents drifted to their current positions from Pangaea. Okay, so post Pangaea, all the continents separated, and then they're now where we see them. He also argued that the continents broke through the ocean crust. Okay, when he said broke through, he basically just means they just kind of forced their way through oceanic crust to move wherever they were moving to. Now, that wasn't a very good explanation, because ocean crust, which is predominantly basalt, is really tough stuff. Okay, and so physicists were able to come out and say, yeah, that's not going to happen. that's not the correct way that it happens. It's impossible. And he also argued that the moon, the pole of the moon, played an important role with this moving of the continents. So he thought that maybe the pole of the moon is what caused the continents to move and break through the ocean crust. And that was pretty quickly debunked as well by physicists. So if you guys have ever seen the Big Bang Theory show, where you have the geology department and the physics department duking it out and making jokes, it is kind of true. There is a little bit of a rivalry to that. But anyways, so you might be familiar with the process of the pole of the moon. Okay, that affects tides in oceans. Okay, but it's powerful enough to do that, but the pole of the moon is not powerful enough to affect movement of the continents. So really, Wegener's main thing was that he was not able to provide a credible or reliable mechanism to explain why continental drift happened, though he did theoretically have the basic concept correct. Okay, so that essentially led into what we call the theory of plate tectonics, which really came about in the 60s, the 1960s. Okay, and that was a revolution in geology because it really summed up everything. Okay, and as we're going to go through this class, you're going to see that pretty much every geological process has some sort of link to plate tectonics theory. Okay, so plate tectonics theory, by definition, is really just the process of moving plates around Earth. Okay, so we're going to talk a little more about that as we go through here. So first, to understand plate tectonics, we need to understand the material in which these plates rest in. Okay, we have continental plates and oceanic plates. Okay, continental plates tend to be made up of the lighter colored rocks and minerals, so the more felsic material. The ocean floor predominantly made up of the mafic or darker colored minerals and rocks like basalt. Let's see what's some other stuff. The ocean crust, the basalt, also tends to be a little denser than the continental plates. The continental plates tend to be thicker. Okay, but the thing the thing that brings the two together, at least relates to both, is that both continental plates and oceanic plates ride on top of this kind of putty-like consistency, like a hard putty-like consistency of kind of semi-molten but mostly solidified material. It's very hard to describe this material, which is in a layer called the asthenosphere. I just describe it as a hard putty-like consistency where the plates can still, where it's hard enough where they won't sink into this material, but it's soft enough where they can move around within the material, and they will float in on the asthenosphere because the asthenosphere is denser material than the continental and ocean plate material. Okay, so that's why they don't sink. They essentially float, or they ride on top of this asthenosphere. So the asthenosphere is a very important layer in Earth's layering, whatever. And I'm going to talk, pretty good amount about it. We'll keep coming back to it because the asthenosphere, like I said, is just very important. Okay, at least for plate tectonics. All right, so in terms of plates, tectonic plates, okay, there are really, I think, maybe 10 major plates, and then there's a handful of other, actually more than a handful. I forget the number. It seems like they keep realigning things up, but there's, let's just say, a handful of minor ones that range from decent size to pretty dinky. But the key is that they're all individual plates, and they all have boundaries. Okay, so they all, which you're going to see here in this diagram, the boundaries are represented by black lines with various symbols. Those are called plate boundaries, and it's those boundaries between the two plates where the geological activity is going to occur. And the key thing here is that pretty much all major interactions, geological activity and interactions occurs at plate boundaries rather than middle or the interior of plates. Okay, I'll show you here a little bit later that there are a couple outliers, but I would say 99% of activity is at the plate boundaries. Okay, so we're going to look here at the different plate boundaries. Okay, there are 3 different types, and then one of those types is broken down into kind of 3 different subtypes. Okay, just to make it a little more confusing for everybody, but you'll understand the method of the madness when we get to it. So let's start with divergent plate boundaries. So at this boundary, there are 2 plates and they're separating from each other, or they're pulling apart. They're diverging. Okay, so where they diverge is called a rift valley here, and what you're seeing is basically magma that is deeper down, okay, even below the asthenosphere. It's since magma is lower density than a lot of the other material in the asthenosphere, magma has a tendency to be kind of a buoyant blob, and it slowly rises within all that material towards Earth's surface because it's less dense. So eventually the magma makes its way all the way up to Earth's surface, and then when the two plates pull apart, it leaves an opening, okay? And that when that happens, that opening, you see lava, the magma changes to lava technically, and then you see the lava come out of the crack and fill it in, and then it'll dry and form ocean floor, okay? Think of this process as like when you have a wound, like a cut, and you accidentally put pressure on both sides of the cut and it reopens the wound and you start bleeding again. Same process where this would be skin on the both sides, and then this middle part, the rift valley, would be where the blood is. Okay, so that's how divergent plate boundaries work. Most of them are underwater in the middle of the major oceans. There are a few that form on land, such as Iceland, okay, but those are pretty rare. But if you ever do get to Iceland, it's definitely worth seeing, because it's something that if you can't see it there, you're never going to be able to see it in the ocean for sure. All right. The next type of plate boundary is convergent plate boundary. So this is where two plates converge, or they basically smash together, they collide. Okay, so this has three different kind of subtypes. And the subtypes are categorized based on the type of crust. Okay, so what each plate is made out of. So first we're going to look at oceanic to continental plate convergence. So this, an example of this situation is the Washington and Oregon coastline, where there's a plate boundary just off the coastlines. And then landward, there's a mountain range, a volcanic mountain range called the Cascades, that runs parallel to the plate boundary itself, so north and south. Okay. So anyway, I'm getting a little bit ahead of myself here. But with the oceanic to continental plate convergence, like I said, the oceanic crust is made up of those denser mafic materials. So it is naturally denser than the continental crust. So when these two meet, when they collide together or converge, the denser of the two is always going to go down. And the term for that is subduct. Okay, so to subduct beneath, the denser one will subduct beneath the less dense one. Okay, so that's why you're seeing this oceanic plate subduct down underneath the continental crust. And it just keeps subducting until it gets below the asthenosphere, and until it gets hot enough to fully melt that plate. Okay, and at that point, what you're seeing here with these kind of orange blobs, that's actually magma, that low density magma that's rising upward toward the surface. Again, it's rising upwards because it's less dense than the material that it's encased in. So it moves up to land and then emerges at Earth's surface, usually in the form of like a magma chamber beneath the volcanoes. Okay, so there are volcanoes in Washington and Oregon in the Cascades. I'm not sure how many, probably 15, 20 total at best. And they've been pretty inactive, but they are nonetheless volcanoes, and they have erupted in the past. So like Mount Rainier, Mount Baker, can't think of the one by Portland, but anyway. So that's kind of the basics of how this situation is set up. Another thing about this, the oceanic to continental plate convergence, is there's a trench, okay, a deep trench where the subducting oceanic plate is beginning its downward descent. So it just creates a trench. Okay, think Mariana's Trench, but that doesn't apply to this specific situation. But I mean, it's the same type of trench. Okay, it's just a very deep trench-like feature. And then also you have, like I said, the volcanic mountains that run parallel to the plate boundary. The trench also runs parallel to the plate boundary. Okay, and then you can see here the asthenosphere. Okay, so we have the crust riding up on top of the asthenosphere, kind of floating. Okay, the second type of the convergent boundary is the oceanic to oceanic plate boundary. A lot of it's the same as the other one, except here we have convergence of two oceanic plates. Okay, now what's going to happen is the denser of the two oceanic plates is going to subduct. So whichever one that happens to be. Same situation where you have the trench and you have the parallel volcanic features, but rather than the parallel volcanic features being a mountain type appearance of volcanoes, these are volcanic islands. It's called a volcanic island arc. Okay, they form parallel to the plate boundary and the trench. And the formation itself of the magma that is that feeds these volcanic islands occurs the same exact way as we saw with the continental to oceanic scenario, where you have the downgoing subducting plate, gets deep enough down where it's hot enough, melts it, the lightweight magma moves upward and fuels volcanoes. Okay, so very similar process. Just make sure you understand the difference between volcanic island arcs and continental volcanic arcs, which is here in this situation, this environment. And then lastly, for the continental or the convergent plate boundaries is the continental to continental plate convergence. This is where you have two continental plates smashing together. Okay, the last major instance where this happened, actually it's the last known one geologically, is when India crashed into Eurasia. Okay, and in that process, what happened was convergence does theoretically occur, but because we're talking about lightweight rock crashing into lightweight rock, what happens is the rock typically is more likely to just drive upward rather than plate being subducted. So it's kind of like in this situation, it's a lot like the two just kind of smash together and then the land gets driven upward. That's pretty much how these work with just a minor little bit of subduction occurring. Okay, as you can see here in this picture, when this plate officially starts to subduct, okay, this right here is ocean crust, because if you look up here, you can see this was ocean up here. Before India crashed in Eurasia, there was an ocean basin in between them. So once that oceanic crust fully subducts, and then you have the leading edge of this continental crust smash into this continental crust, you can see it basically gums up the system and it essentially stops subduction. So that's what causes the driving up of the land into a mountain range. So that's the Himalayas presently. And because India is still currently pushing northward, the Himalayas are still rising. Okay, they will continue to rise, and they do year by year by probably a millimeter or something. You know, really, really tiny difference. But they'll continue to rise until various factors cause them to stop. Okay, we'll talk about those factors throughout the class. But right now, I don't want to get specifically into it. Okay? So yeah, so that's the third type, or I'm sorry, the third type of the convergent plate boundaries. The third type of the plate boundaries I know this is a little bit confusing, is called a transform plate boundary. So in this case, when you have two plates still, but rather than the two plates converging or diverging, the two plates are merely just moving in relation to each other along a straight line. So up here, if you can see, we have the Pacific plate and the North American plate with the San Andreas Fault here in the middle. The plates are, one is moving south, one is moving north, and you can see that they're not crashing into each other, they're not pulling apart, they're merely just sliding past each other, okay? And that's pretty much how a transform fault works. Okay, so at the end of this chapter, I think it is, we'll talk a little bit more about plate tectonics in the future, so you'll be able to see how the San Andreas Fault is going to change. Okay, before I move on to ocean floor drilling, are there any questions on anything? Okay. All right, so evidence for plate tectonics. So ocean floor drilling by ships was one of the predominant ways to collect data back in the early 60s when plate tectonics theory was still quite young. Basically, ships would drill cores down in through the sediment and the basalt. Okay, so for the ocean basins, the ocean crust itself is typically basalt. Okay, I'd say 90% is going to be basalt. Above the basalt is going to be a layer of sediments that have collected. They're basically sediments that have originated from continental areas, usually, that have been deposited into the oceans, and they're light enough, fine enough in size where they just kind of float in the water and then eventually settle down to the bottom of the ocean. Okay, so if you were to go to the bottom of the ocean, most likely you would encounter sediments rather than basalt, except in one place, and that would be the plate boundary. Okay, so right here is the divergent plate boundary where you have these two plates pulling apart. Okay, now where that happens, that divergent plate boundary, that fresh basalt is produced. Okay, and there's no sediment. Okay, there's no sediment because there has not been enough time for any sediment to collect there. But if we go you know, on both sides here, think of a mirror being here at the divergent boundary, and what you're seeing on both sides is the same exact thing, which is typically true. You're seeing the sediment deposits getting thicker and thicker as you go away from the plate boundary and get out toward the continents. That's because that's older basalt. There's been a lot more time for sediments to settle down and collect. Okay. So that was evidence that was used. They say, okay, well, there's a lot more sediments here on top of this basalt, so that must mean that it's a lot older than the stuff here at the plate boundary. Sediments take a long time to settle down and deposit. Okay, then the oddity that I said about volcanic activity in the middle, or at least just on the interior of any plate. These are called hot spots, technically, when they emanate. But hot spots really originate as a result of what's called a mantle plume. A mantle plume is an isolated upward movement or upwelling of magma from the, typically from actually deep down at the mantle core boundary, so way deep down. For some reason, that's where it originates. Big blobs of magma, again, because they're lightweight, they move straight upward, and they basically burn a hole through the crust, and they create volcanoes, okay? And it just so happens that this occurs not at plate boundaries, okay? It's not, the concept of the mantle plume is not fully understood why this happens in the middle of a continent, because it doesn't happen in every continent, and there's no method to the madness. It just occasionally randomly happens. So there's a lot of ongoing research on that. explain. But where that mantle plume finally reaches Earth's surface is called the hot spot. So the location on Earth's surface where the mantle plume emanates at land. Okay, so that typically results in the production of volcanoes if it's on land, or volcanic islands if it's in the middle of the ocean. So Hawaii was formed from mantle plumes, or from a mantle plume. Actually, let me back up. Yes, yeah, it was formed from one mantle plume, but I guess you could say it has multiple hot spots, but the way to describe it, I guess, is that you have currently the island that's sitting over this mantle plume is the island of Hawaii. That's the youngest and biggest one. What's happened is the Pacific plate has actually moved to the northwest, or up in this direction, okay? And so what's ended up happening as the plate moves, the mantle plume remains stationary, and thus when the plate moves, the mantle plume burns a hole through the crust at that point and creates a new island. Okay, so basically what you're seeing is here progressively aging islands. So here's the oldest islands up here, and then if you look at the dates, they get progressively younger and younger and younger until you get down to the island of Hawaii, and that's where the mantle plume is present day. Okay, so that's kind of how a hot spot works. All right, I'll go ahead and stop for any questions. All right. Okay, so convection. Okay, convection is something, the process of convection is something that you absolutely need to understand, because it is really at the core of how plate tectonics works. And it's not hard to understand. So convection is simply the transfer of heat, okay? And that transfer of heat is driven by differences in temperature and density, okay? Remember that density basically means weight. So I like to explain it with the boiling pot analogy, where you have a pot of water on a burner boiling. That doesn't need to be boiling technically, but the key is that you have the hottest or the warmest water down here at the bottom, right next to the burner. That's your heat source. Okay, think of Earth's interior as the heat source, because it is. Well, what happens is warm things are less dense, so they will rise. So this warm water down here is going to become less dense, and it's going to rise naturally. So it'll rise up to the top. And what happens is up at the top is the cooler material, because it's the furthest away from the heat source. But what's going to happen is, because the cold water and the warm water are touching each other, they're in direct contact, when this warm water rises, it's naturally going to push that cold water out of the way. Okay, and as that cold water gets pushed out of the way, it generally starts to get pushed down in a downward fashion, in which case it gets closer to the heat source, which means that it warms up. Okay, and so what you end up having is this circular motion of warming and cooling. Okay, and because all the water is in direct contact with its neighbor water molecules, the whole system is driving itself in a circle as a result of the temperature difference and the density difference. Okay, so that circular movement, you're going to learn that to be called a gyre. Okay, also a convection cell. Those are two different terms that you're going to see it called. Okay, even in when we look at oceanography, you'll see the gyre, because that is a process in the oceans as well. All right, so plate tectonics in the future. This is kind of interesting. So this is not proposed, but this is what they think the continents will look like in 250 million years. So most likely a supercontinent again. Um, that supercontinent will also have moved a little bit north, but not a whole lot, because we'll notice that the let's see, yeah, a little bit north. But one of the more interesting things is the situation with the San Andreas Fault, because land west of the San Andreas Fault is the Pacific Plate. Land east is the North American Plate. And so the Pacific Plate is moving northward in relation to the North Atlantic Plate. So that means that 250 million years from now, the Pacific Plate will have moved far enough north that it will have carried Los Angeles all the way up to and set it neatly next to San Francisco. Okay, so essentially suburbs of each other. It'll be a mega city, so maybe it'll be bigger than the Tokyo. I love the joke, but all jokes put aside, 250 million years in the future, I don't think any of us will be alive at that point. But it's kind of cool to think about how these things work anyways. Also, Africa will basically what's happening between the Eurasian plate and the African plate is that they are closing in on each other, okay, as a convergent plate boundary. So Africa is going to eventually collide with Eurasia. That will result in the closing of the Mediterranean. So the Mediterranean will disappear, and then what will happen is, because it's a convergent plate boundary, a series of volcanic mountains, much like the Cascades, will form, most likely in the northern, they'll form in a east-west linear fashion, probably just off the shore of present-day like southern Europe. I know the Mediterranean isn't perfectly perfectly straight across, so it's kind of hard to say, but so mountains will basically just form where the Mediterranean currently is. I guess that's the major thing to get out of it. Also, we know that India in the past moved northward and crashed into Eurasia. That created the Himalayas. Also, but currently there is a northward trajectory of the islands of Australia, New Guinea, Indonesia. Yeah, basically all the South Pacific islands. They're all moving northward, okay, and they will eventually crash into Southeast Asia, pretty much just to the east of India. So that would be like like Burma. I don't even know if it's called Burma anymore. Yeah, basically like yeah, Southeast Asia. So like I guess Vietnam. I wish I was better at geography, but and so what will end up resulting in is just like the Himalayas, large continental mountain range will be driven up in Southeast Asia in 250 million years. Okay. All right, so that's it for this. Yeah, that's it for this chapter. Are there any questions I can field about anything that we talked about in chapter 4? Let me see here. Okay. Right. Nothing in the chat. All right, so then we'll go ahead and continue on to earthquakes and Earth's interior. So earthquakes, okay, very simply explained as ground shaking, okay, and that ground shaking is caused by the sudden movement of essentially one block of rock in relation to another. Now, when I say one block of rock, theoretically, it is a fault boundary, okay, but typically earthquakes are more localized scale, so it's not correct to say that earthquakes occur at like plate boundaries along the whole plate boundary, because they don't, okay. Earthquakes tend to be localized, but earthquakes do also occur inland, Okay, earthquakes don't just occur at plate boundaries. It's just that they're very rare inland. But there are some instances in the geologic past where there has been some various mountain building events that have resulted in the formation of very minor faults. Okay, but I'm gonna put that away because you guys don't really need to know that. I want to focus on the big picture here. So let's just keep it as most of the geologic natural disasters occur at plate boundaries. Okay, we'll keep it at that. But earthquakes, like I said, they tend to be a little more localized. They're not going to occur along the whole fault all at once. Okay, but anyways, I'm kind of getting ahead of myself. So what causes an earthquake to occur? So let's go through this picture here, and I'll explain. So you can see that there's a fault here. Okay. And there's two blocks of rock. There's one on each side of it. One is moving northward, or upward, I guess. The other is moving downward. You can see that here. So what's happening is over time, because they're moving in different direction, they're actually putting a strain on each other where they meet. So they're putting a strain on the fault. And what's happening with that strain is it basically means that they're stuck together still, and they're deforming, or they're behaving kind of ductily. So they're stretching, but without breaking apart. And that's what you're seeing here is the buildup of strain. Eventually, that buildup of strain will be too much, where the strength of the materials that are found within the rocks will be too much, and then the two blocks will finally rupture and they'll move. Okay, they'll just jolt, and that's what you're seeing here in this picture is the two plates are jolting. They jolt, they release their pressure, and they're moving in different directions. Okay, that is the earthquake itself. Okay, the earthquake is that release of energy, and then the subsequent movement of the rocks, the blocks of rock. Yeah, I think that pretty much covers the basics. So earthquakes can happen before and after as well, but typically the ones before and after tend to be of lesser intensity. So pre-shocks and aftershocks, or rather foreshocks and aftershocks. So the machine that's used to study and pick up the intensity of earthquake waves is called the seismograph. And that's this machine. It's basically, you can see a series of steel parts that are bolted onto some solid surface that is connected directly to either another surface that's solid that's connected to the ground, or they're connected directly to the ground. It could be either one. The key is that they have to be connected. They have to be connected directly to something that doesn't move on its own accord, but will shake when earthquakes occur. Okay, so that's the main thing. So when the shaking occurs with the earthquake, this steel arm has a needle on it, and it basically goes back and forth. And the more it goes back and forth, so the bigger the spike is, the greater the intensity. So the greater the earthquake is. So here, if you can see this big one, this big spike, that's called having a high amplitude. Okay, so the amplitude means it's a real big spike. That means that's when the earthquake is expending more energy. So that's probably the worst part right there. Here is where you're seeing it taper off. Okay, that means it has a low amplitude, so that means the energy is really pretty low. Okay. So there's two different types of seismic waves. Surface waves are either at Earth's surface or they're very close to Earth's surface. They take on a side-to-side shaking type movement, and they tend to be the most destructive of all the seismic waves because they are at Earth's surface. Okay, the other waves, the body waves, tend to occur deep down in, well, at least below Earth's surface, and so they're not as intensive at the surface as these ones are typically. But they cause, surface waves tend to cause a lot of damage because of that side-to-side movement. Okay, so next let's look at body waves. Body waves are waves that travel through Earth's interior. So like I said, you'll never see these occurring at Earth's surface. There's two different types of body waves, P waves and S waves. Okay, so the P waves, the primary waves, that's what you're seeing right here. They take on a compressional type motion, so push-pull, like a slinky being pushed back and forth. Okay, so you'll see that energy moving through the slinky when you do that. Okay, that's compressional. P waves can travel through solids, liquids, and gases, so they'll travel through anything. And that's a great thing because geologists have been able to do a lot of research and kind of extrapolate things because of that. They also tend to have the greatest velocity of earthquake waves, but because they're typically originate lower, deeper below Earth's surface, their energy tapers off as it heads up towards Earth's surface. The secondary waves over here, you can see they do like a shaking motion, or kind of like when you have holding a rope and you whip it, you get that kind of sideways S shape. Okay, that is a shaking motion. So just different way that the energy emanates. It's not as powerful as the primary waves. But the interesting thing about S waves is that they travel only through solids, so they will not travel through liquids or gases. And that's very important when we go to look at the composition of Earth's interior, is you're going to see that one of the layers of Earth's interior is actually a liquid. Okay, just terminology basically here. The focus is exactly where the earthquake originated, and that's always underground somewhere. Okay, the epicenter is the land area directly above the focus, and so the land area directly above where the shaking is the most intense for that earthquake. Okay, so usually in the news, I usually hear the term epicenter used, which is fine, but just know that the focus is the actual place, subsurface, where the earthquakes occur. All right. So what we're going to do now, I'll just stop and actually see if anybody has any questions before I move on. Okay. Okay. So now we're going to take a look at how we find where earthquakes occur, because that's very important. So the basic answer to that is because P waves move slower than S waves, that's backwards, P waves move faster than S waves, we can actually track where they occurred at, okay, because they have a known velocity. They move at a certain speed, a known speed. So to do this, we need at least 3 recording stations. It can be more, but at least 3. And what we're going to do is we're going to take a seismogram, okay, basically the reading from the seismograph tool, the machine. And what we're going to do is, let me go back. We're seeing here where we have the first waves come in, okay? The fastest of the earthquake waves is the P wave. And here's where we're seeing the first P wave arrive. We're seeing it spike with the highest amplitude, and then it's kind of tapering off. Okay, so we continue over time and notice that each one of these little columns represents 1 minute of elapsed time. And there's 5, last I checked, there was 5 of these columns between when the first P wave arrived and when the first S wave arrived. Okay, so because the S waves arrive later, we know that, okay, they arrived 5 minutes later at this specific location. Now every location is going to be different. Okay, if you're closer to where the actual earthquake occurred, the elapsed time here is going to be shorter. Okay, if you're way further away, it's going to be longer. Okay, so what we're going to do is we're going to take the 5-minute interval here, and we're going to measure it, literally measure it in whatever centimeters, inches, eraser tips, whatever the heck you want to measure it in, doesn't matter as long as it's accurate. And you're going to bring that measurement over here to this chart, and you're going to flip it upside down so that it's up and down. Okay, so that specific measurement correlates with it has to fit perfectly between these two lines. And so this right here is where that length fits perfectly between those two lines. So what we're going to do is we're going to go straight up, and we're going to see, oh, okay, so that earthquake is approximately 2,100 miles away. It occurred about 2,100 miles away from our recording station. Okay, so that's how it's done. And each of the 3 recording stations are going to go through that same process. They're going to come up with a distance, their own specific distance. So if we move over here, we can see there are 3 recording stations, and what they're doing is they're going to a map, and they're figuring out on the map where 2,000 miles away is, and they're taking the compass, the geometric compass, and they're drawing a circle that's 2,000 miles everywhere along that circle. Okay, so like with this green one, for instance. So each of the 3 stations does that, and then the interesting thing is, if you do it correctly, all 3 will intercept at 1 point only, and that will be your earthquake location. So right here, that red star, all 3 they meet, and that's where the earthquake occurred. So it's actually a pretty cool way to figure out where an earthquake occurred. Okay. So later, I believe we're going to do the lab that you're actually going to have the opportunity to calculate that, but it's pretty easy stuff. So sorry, you won't do the lab. This is the non-lab class. Boy, I get mixed up these days. All right, so earthquake magnitude. So the magnitude is the amount of energy that's expended. Okay, really, that energy can be represented in one of 2 different scales. Okay, probably more familiar with Richter scale. Okay, that's a 1 to 10 scale, with 1 being very low energy expenditure, 10 being very high. Okay, and with each number jump in that scale, there is actually a 32-fold increase in energy expenditure. So we're not talking linear here, we're talking logarithmic. Okay, so each step is 32 times more energy. So that means when you get up here to 8, 9, 10, you're talking a major earthquake with a lot of energy release. Look at all those commas in these numbers up here. That's a lot of energy. All right, so that's the Richter scale, pretty cut and dry. The moment magnitude scale is a little bit different, whereas it measures the displacement of the fault. So the rock blocks on each side of the fault, it measures how much they moved in relation to each other. And then it also adds in Um, what is it? A little bit. A little bit to calculate it includes the amount of destruction that occurred. So the moment magnitude scale also has a little bit of a societal aspect to it. So um, in that case, the Richter scale is really just the cut and dry, real clean answer, whereas the moment magnitude scale is a little bit more people friendly. Okay, in terms of predicting earthquakes, so short range predictions, both predictions are really not very reliable. Okay, but short range predictions, um, I would say they're a little more reliable because oftentimes there are warning signs. These are called precursors. So oftentimes little grumbles of like little dinky earthquakes that will occur before the big earthquake. Sometimes the land area adjacent to the fault will actually begin to arch upward because that's a sign that there's strain being put on the fault. Okay, so the land is starting to arch upward, and monitoring with GPS can determine if that's happening. Also, strange behavior in wildlife. This may sound like a weird thing, but it has been shown to be true many times. So if you're ever in that situation and you see wildlife acting erratically, I guess it's best to just say, hey, something weird is going on. Maybe, try to take a step back and just look to see what it might be. But with an earthquake, of course, you wouldn't know until it happens. So that's something interesting to look into. So long range forecasts, we just know that earthquakes are repetitive. Okay, so they're basically every year, any given segment of a fault is going to be assigned a probability that it will experience an earthquake within a certain number of years. That's pretty much what that is. It's really not very, like I said earlier, along a long plate boundary like the San Andreas, what's going to happen is you're going to have earthquakes at different parts of the fault boundary at different times because stress is building up, resulting in excessive strain in various degrees at various parts of the fault. Okay, so every piece of the fault is different than others. So you never know when an earthquake is going to happen, really. Okay, so that's kind of the big picture thing. All right, so that's the end of the earthquake part. Are there any questions on earthquakes? Let me do this real quick. So I brought up, I still have it up, yeah, I do. The earthquake.usgs.gov. That's the U.S. Geological Survey's GIS platform for the most recent earthquakes. And you just go on and you click on the orange dots, it'll tell you about them. So like here we have a magnitude 2.5 and then it gives its location. So I will tell you that any earthquake below a 3 typically can't be felt. So it pretty much has to be above a 3. Okay, so see if we can find one above a 3. No. Come on. 5.0. There we go. So yeah, anything above a 3 you can typically feel. Anything below you don't feel it. So here's one that happened Oklahoma. Okay, typically that's not normal. Okay, but I will tell you that because of the geologic structure of that area, there was some past very ancient mountain building events that happened, and the area has over several billion years basically eroded down those mountains, okay, into the flatness that we now know Oklahoma and Arkansas to be. So yeah, there are oddities, but there's always an explanation. Okay, so earthquake.usgs.gov if that interests you. I did once feel an earthquake when I was at my sister-in-law's house in the Los Angeles area. And everybody's got a pool out there, so she had a pool. And I'm looking, I thought I felt just like a slight vibration. And I look at the pool and there's vibrations, so water ripples. So I was like, oh, that's pretty cool. Be able to actually get to see it for once. All right, so Earth's structure. Earth is really broken down into the crust. That's the plates, basically. That's what we live on, and the ocean crust. Below that is the mantle, and then below that is the core. Okay, so it's broken down a little bit more than that, so I'll explain it as we go along. So the mantle, so we have the lithosphere is self-explanatory. Like I said, that's where we live. The mantle is located between the crust and the core. Okay, so the lithosphere, and I wish they wouldn't do this, but technically, a little bit of the upper mantle is considered to be part of the lithosphere. I don't know. I don't really, I try not to teach it that way because it just makes more sense. But it is technically true. But let's just say we're gonna lump the plates and the mantle separately. Okay, just because that makes it the easiest to really remember and understand. Okay, so in the mantle, we have the upper mantle, the uppermost part, that's called the asthenosphere. Remember, that's that very hard putty-like consistency material that the plates ride on. Okay, so the very important asthenosphere. Below that is the mantle, okay? You've got the upper mantle and the lower mantle. That material tends to be made up of, still made up of rock that is very close to being fully molten, but still considered to be in rock form, technically. So very hot, capable of flow, which means that convection can occur. Okay, if it's capable of flow, that means convection occurs. So Earth's core, there's the inner core and the outer core. The outer core is that liquid layer that I talked about. Okay, so it's made up of liquid nickel iron alloy, and you can see it's very dense. Okay, basically what happens in terms of density of material is up here at the surface is the least dense material. As we go down into the mantle, the material gets more dense. Outer core, it gets even more dense, and then finally the inner core, it's the most dense. Okay, so a density increases as you go down towards Earth's core. That's the big picture. So high density, okay, 11 grams per cubic centimeter. That's around 3 to 5 typically for the continents. So quite a bit less dense. But like I said, it's a liquid, and it's a liquid that actually circulates in circles around Earth. Okay, and that, as a result, creates what's called a dynamo. It's basically a magnetic field that produces electricity. Electricity. And that electricity is in the form of a magnetic field, essentially. So Earth does have a magnetic field. Okay, you can't see it, but you can, you know from magnets, it has a north-south fields. And that magnetic field is very important because the sun sends out a lot of very harmful radiation, okay? We're talking things all the way up to like gamma rays, okay? Very harmful stuff. And then everything else, all the way down to just visible light, you know? So what happens is the Earth's magnetic field basically filters out, it blocks the more harmful stuff, okay? So what's left that is allowed to go through the magnetic field is typically the safer stuff. You know, like UV isn't really the safest, but there's a whole lot worse stuff that gets reflected and sent back out to space. Okay, so so that's so the outer core is liquid. The inner core is a solid. Okay, very similar composition of metallic iron with some nickel. I guess I should say it actually behaves like a solid because normally it would be a liquid. Okay, but because of the massive amount of pressure that's put on it, it behaves more like a solid than it does like a liquid. So it's assumed that yes, technically the inner core is a solid, whereas the outer core is a liquid. You got to remember, there's just a lot of pressure from all the way to this material above it pushing down. Oh, okay. Guess that's it. I thought there was more after that, but okay. So are there any questions on anything? Let me go back here. No questions. Okay. All right, well then that's it for today, for this week actually. So we'll resume next Wednesday and we will cover chapter 6. Okay, so make sure you read chapter 6, watch the Earth Revealed videos listed in the syllabus. And that's it. So everybody have a good weekend.
Bye, thank you.